Hi, I'm Grant Graydon, and I figured I'd do one of your homework problems here. This is the last homework problem from Dr. Sue's most recent homework. And in this problem, we're asked to find the maximum power that can be transmitted through this hollow steel shaft, and we're also asked to find the corresponding angle of twist of the shaft. So, I wrote down on the left here all the equations I thought I'd need. So, we're going to be making the assumption that we're within the elastic range so that we can use the equation of shear stress is equal to shear modulus multiplied by that guy right there. So, why don't we start out with figuring out the maximum power that can be transmitted. So, what do we know? Well, we know what we have a value for G, we have a value for tau, and we have omega is equal to 240 RPM. So we know this, or sorry, we do not know our torque, but we do know tau, and we can also pretty easily figure out what C is and figure out what J is. So we can use that to figure out what our torque is, and then use that to figure out how much power we have going through our system. So why don't we start? But before I start, I want to do something pretty important here, which is I want to convert from RPM to radians per second. So to do that, we can say that, well, let's try and figure out by hand here how to convert from RPM to radians per second, where the thing comes from. So 1 RPM is equal to 1 revolution per minute. And if we multiply that by 1 minute over 60 seconds, minutes, those units cancel out. We're left with 1 over 60, so that would just be 1 revolution a second. It's equal to 1 over 60. And then we can also say 2 pi radians is equal to 1 revolution, which makes sense because, if you have a circle like this starting from here, go all the way around. If you remember from the unit circle, that'll be 2 pi to go across the whole thing in radians, and that's 1 revolution. So you end up with 1 RPM is equal to 2 pi radians over 60 seconds. So that means omega is going to be equal to, let me go grab my calculator. Omega is equal to 25.13 radians per second. I'm just giving 2 decimal places here, so it's approximate, but... And why don't we as well put down values for our shear modulus and shear stress. So 77.2 GPa is equal to 77.2 times 10 to the 9th pascals. And 50 MPa is equal to 50 times 10 to the 6th pascals. So now we have all our knowns over here. So let's start out by working from this equation. We should also recall that J for a hollow tube, I believe, is equal to pi over 32 times d to the 4th minus d to the 4th, where this is the outer diameter and this is the inner diameter. So I'm going to just rearrange the equation and solve for torque. All right. So we're going to want to work in SI, but we can tell our OD here is 60 millimeters, and our inner diameter is 25 millimeters. And C is just going to be from that center farthest distance out. So the farthest distance out is 60 millimeters divided by 2, which is just, the radius of our outer diameter. So just plugging in our numbers here, our shear stress is equal to 50 times 10 to the 6th pascals multiplied by pi over 32 times our outer diameter of 64 divided by 1,000, so it's in meters. And then our inner diameter divided by 1,000, so that's also in meters. All divided by C. Oh, also this should be 60, not 64. So yeah, C once again just going to be 30 because it's the radius of that outer diameter. So 30 divided by 1,000 meters. And plugging that into my calculator here, should get torque is equal to 2056.66 Newton meters of torque. And now we're going to want to apply the equation of T is equal to P over omega. And we're just going to solve for our power. So power is equal to torque times our angular velocity. And we converted earlier to radians a second, which is what we need. So times 25.13 rad sec. We end up getting that the power required, or the maximum power this can drive, is 51,683.86 watts. Which, if we just move that into kilowatts, it's about 51.68 kilowatts, which is a reasonable figure. Now, to figure out our angle of twist, how are we going to go about that? Well, once again, we know our shear stress, we know our shear modulus, and what we don't know in this equation right here is just the angle of twist, which is nice to work with. So, if we go ahead and substitute this right-hand side into there, we end up with tau is equal to G times C angle of twist over L. And now we just have to solve for our angle of twist. Now, working from here, we have 50 times 10 to the 6th pascals multiplied by the length of this, which we're given as 5 meters. Multiplied by our shear modulus, which is 77.2 times 10 to the 9th pascals, multiplied by, just like earlier, 30 over 1,000 meters for that radius. So we will end up getting, let me plug it into my calculator. Our angle of twist equal to 0.108 radians about, which if we convert that into degrees by doing 180 over pi, we get 6.18 degrees approximately, or about 6.188 degrees of rotation for our angle of twist. Alright, so I hope this helped, and I hope you have a nice day.